So up to this point, we've talked about solving linear equations and then graphing those equations. And we discussed solving linear inequalities. So now let's talk about graphing linear inequalities. We also said before that dealing with linear inequalities is actually pretty similar to working with linear equations. If you compare the linear equation here on the left to the linear inequality on the right, you'll notice that the equations themselves look similar, and that there's also some similarity between the graphs. Let's talk a little bit about how they differ. For the left-hand equation, y is equal to 2x plus 1, if you set x equal to 0, you can see both from the graph and just by calculation that the value of y will be 1. So why does the graph look different for the analogous linear inequality? Well, let's do the same thing here. Let's let x be equal to 0. The expression we're left with if we do that is that y is greater than 1. Now here's a question for you. Can y actually equal 1? If you said no, then you're right, because this is a greater than inequality, not a greater than or equal to. So again, taking a look at x is equal to 0, we see that y can be greater than 1, but not equal to it. That's why we have a dashed line here. And we're going to go through this a little more thoroughly in a few minutes, so don't worry. We're just making some observations right now. So when x is equal to 0, we know that y can be greater than 1, but it can't equal 1, hence the dashed line. So why is the graph shaded like this? Well, if you think about what we're looking at, y can be anything greater than 1. So when x is equal to 0, y can equal 2, it can equal 4, it can equal 6, it can equal 8, or anything in between. So any point in between can be the value of y. And if you go to the negative side of the x-axis, or the positive side, you'll get similar expressions. And what you end up with is if you put dots on all these points, you'd end up with a shaded area. Let's take a closer look. This is such a simple problem that what I'd like for you to do is to take each one of these points and solve the inequality for y. Then when you're done, come back and unpause it and we'll continue. Okay, so the answers you got should agree with what we have in the table here, and should also agree with the graph on the left. So we see that when x is equal to negative 1, y must be greater than negative 1. So the value of y can be any of these values as long as it's greater than negative 1. And from what we just saw here, when x is equal to 0, y must be greater than 1. When x equals positive 1, y must be greater than 3, which is roughly this point here. The value of y can be greater than 3 when x is equal to 1, but it can't actually be 3. So what's the difference between the graphs we've just been looking at versus greater than or equal to or less than or equal to graphs? Well, actually, they would look pretty much the same, except that you wouldn't have a dashed line, you'd have a solid line, because the solution set at that point would be including the values of y that we get when we plug in x. As always, please take a look at any solved problems lectures and work any quizzes related to this topic to help solidify your understanding. We're going to take a break here. When we come back, we're going to talk about some common patterns that you see in graphs of inequalities.